In this video, I want to talk about one of the homework problems, and that is problem number 2, because I have a lot of students coming in and asking about this problem. So I have copied this problem here. The problem asks for the magnetic field due to a sheet of current. And if I am to illustrate this problem in Cartesian coordinate system, it would look something like this. So this would be my coordinate system. I have x, y, and z directions, and all of my current is flowing in the y direction, as is indicated here, and they are distributed over a width of w. We are interested in finding out the magnetic field at the point P, which is 0, 0, z here. Okay, so this is where my current is distributed. And obviously this is a surface current distribution, and in order to find out the magnetic field H, you would have to use an integration of Biot-Savart's law. So in order to do that, we typically would follow normal procedures by picking out a small surface element, because in this case it's a surface current distribution, and I call it ds. In the Cartesian coordinate system, this little surface would be actually ds z, because z is not changing. So we would be interested in finding out dh due to this little surface dz. Okay, and this little surface carries a little current segment. A lot of the students are confused when they are dealing with surface elements, especially when they're looking them up in the table. The table would actually have a direction for the surface, but in this case you're interested in the total current. In other words, we're interested in Js times dsz. The direction of this current is determined by the direction of the charges, or the direction of the flow of the charges, rather than the direction of the surface. So in this case we're only interested in the magnitude of the surface. And if you look it up from the table, dsc would simply be dx times dy. And it's also obvious from this illustration. This side would be dy, this side would be dx. From Biot-Savart law, my dh, or actually my total h, so I can directly write out my total h vector, is given by 1 over 4 pi surface integration, because we're dealing with a surface current distribution, of Js, which is the surface current density, cross r hat being the unit vector of this vector that points from the source to the point of observation. So this is r vector, and r hat basically means the unit vector of it, over r squared, now r being the magnitude of this r vector, or in other words the distance between the source and the observation point, integrated over the surface ds, which is essentially this guy. Okay, so before we can find out r hat, we probably need to find out the expression for this r vector. And an easy way to do that is to project this r vector onto the 3 axes. So if we project it onto the z-axis, it's pretty clear the z magnitude for the r vector would simply be this much. Okay, so the z component would be z hat. Now if we project it to the x-axis, it would be projected this way. Then this is simply the x coordinate for the current element. So that would be x hat. And similarly, if we project it to the y-axis, it would be y hat. So that gives us the vector expression for r vector. Its magnitude r in italic would be the square root of x squared plus y squared plus z squared. And the unit vector would simply be the r vector being normalized by its magnitude. So that would be x hat plus y hat plus z hat over square root of x squared plus y squared plus z squared. Okay, now I think we have everything to evaluate this equation here, so I'll just move it down here. My h is 1 over 4 pi and integration of js, which is in this case already given, it's y hat 5 cross r hat, which is x hat plus y hat plus z hat over square root of x squared plus y squared plus z squared over magnitude squared, so that would be x squared plus y squared plus z squared. ds, as we explained before, would be would be dx times dy. And this is really a surface integral, so it's carried out over the x and y directions. On the x direction, the limit for the integration would be from 0 to w. On the y direction, the limit would be from minus infinity to infinity. Then you can copy this whole thing down here, dx dy. Okay, now this is a rather complicated integration because it not only involves the integral, but it also involves the directions, different directions. So the cross product of these two would have all x, y, and z directions. In other words, you have to evaluate 3 different integrals along x, y, and z directions respectively. So one way to simplify this problem is by looking at it and taking advantage of the symmetry in this problem. So obviously this problem is symmetric across the xz plane. Okay? By doing a similar trick as we did in the class, we can pick a symmetric point across the xz plane. So if we look at both of these points, this current is going to give me a magnetic field that is pointing outwards like that. So this has to be perpendicular to this vector. It has also to be perpendicular to the direction of the current. Then this guy here would give me another vector that point towards us. Okay. Now if you look at it closely, you will see that the y component of these two, so I would call it dh1 and dh2, the y component of these two vectors would cancel with each other. So that tells us, by symmetry, my H field would not have a y component, so this would be 0. In other words, when you evaluate this integral here, you only need to evaluate along the x hat direction and the z hat direction. So that somewhat simplifies this problem a little bit, because you are now doing 2 integrals instead of 3. There is another way of solving this problem that is actually much simpler. To demonstrate that, I have copied my drawings here with my coordinate system and the distribution of the current. We know that in this problem the current is distributed over a plane that extends infinitely to the negative y direction and also to the positive y direction. If we pick a filament of current, in other words, we take a very thin slice along the x direction, I would have an infinitely long line current. If you still remember the example we worked out in the class, if you have a very long line current, essentially it has to be infinitely long, then the H field at any point in space can be worked out very easily by Ampere's law. Okay, so the H field here would have direction in the phi direction with a magnitude of I over 2 pi r, and this comes from Ampere's law. Okay. And now if we can treat this problem that we're trying to solve as a combination of many such infinitely long line current, then we can carry out our integral along the x-axis. So what we need to do is that we pick one of them, which is a very thin line current, and we find out the magnetic field intensity at this point due to this line current. So instead of doing a small segment on the surface, we pick an infinitely long strip of current. Okay, so the magnetic field due to this line current would be given again by the right-hand rule. So I have my I and the R vector, then I know that my magnetic field is going to be perpendicular to both of them. So this would be my H field, or DH, due to this line current. Okay, because of symmetry, we know that this H field can only have a Z component as well as an X component. It would not have Y component because this problem is symmetric with respect to XZ plane. Following this example, we know that for DH, its magnitude is going to be I over 2 pi r, where r is this distance vector. In this case, the current I is simply given by Js times dx, because Js is the surface current density, and dx is the width of the strip. So if you multiply the two, it gives you the total current. And then r, in this case, is given by the square root of this length plus this length. So that's the square root of x squared plus z squared. Now we need to find out the direction for dh. Since we know that it follows the right-hand rule, its direction can simply be given by I cross r normalized by its own magnitude, so that we get a unit vector. Okay, so for the current I, we know that it has a direction of y hat. You can add in the 5 dx, but it will all cancel out, so it doesn't really matter. Cross r. Okay, so now what is this r vector? So this vector, if you project it to the x-axis, you see that it's minus x hat, and z hat. Okay. So for the r vector, we have minus x hat plus z hat. And then obviously you normalize it by itself. So the result of this is z x hat plus x z hat over the square root of x squared plus z squared. And you can verify this by yourself. Okay, so combining all of these, we now know that dh is equal to I over 2 pi square root of x squared plus z squared times zx hat plus x z hat over square root of x squared plus z squared. Now let's plug in the numbers and further simplify it. So this becomes js dx zx hat plus x z hat over 2 pi x squared plus z squared. Okay, so now we have known the differential magnetic field intensity due to a line current, a very thin strip of line current. Now the total H field would be a simple integration over the x direction. Okay, so we would integrate it from 0 to w dh, which is essentially 0 to w js dx. And I'm just copying from over here, 2 pi x squared plus z squared. And I'll leave it to yourself to evaluate this integral.